Good afternoon, everybody. Welcome to sunny Monday afternoon of Chem 1105 with your host, me, Dr. White. Hi, everybody. Hopefully you had a nice weekend. I did, a really nice one. But because of that, I'm a little behind in grading labs. Bad, Dr. White. Bad, Dr. White. You're bad. Uh, but anyways, couple important things. First of all, like I said, I'm a little behind grading labs. By this Thursday morning, I will catch up, have lab scores in Blackboard. I apologize. All right. Let's do this. All right. On this Thursday, I will be giving test number 3. By the way, in July, I give a lot of tests. That's just the way it turns out in summer. And this summer is going to be no different. All right. On this Thursday, I will be giving test number 3. 1, 2, 3. And I'll be giving it online like I've done the other tests. And you'll download the password protected PDF file for test number 3 from the assignment area Blackboard. On Thursday morning at about 8 o'clock or even a little earlier, I will send out the password via email and that should be test number 3, not 1. I'll have to change it later on. Wait a minute, I'll just do it right now. Instant correction. And you'll get another email now because of my mistake. Bad, Dr. White. Anyways, I will send out via email the password for test number 3 PDF file. You'll have until Friday, the 21st, 4 p.m. to finish test number 3 and upload your test number 3 answers as a single PDF file to the assignment area Blackboard. It should take you about 45 minutes to finish the actual test, but guess what? Since we don't have to leave the classroom, that's a lot of reasons why I can't give extra time on tests. Take up 3 hours if you need it. You shouldn't, but go ahead and do it. All right, test number 3 will cover chapter 6, gases, and chapter 5, part 2, solutions, which I should finish today. All right, test will have 20 problems, 9 pages. There are 5 multiple choice. Some of the questions have multiple part, like A, B, and C. And topic area, gases will have 48 points, solutions 57. It adds up to 105. So that means there's 5 bonus points. As always, you'll need a scientific calculator. I reserve the right to anybody who doesn't subtract 50 points, anyone who doesn't follow instructions, or does not upload your test number 3 answers on time as a single PDF file. As I've done the other tests, by the following this Sunday, I will post the scores for test number 3, and I'll also send out an email with your individual points for each answer on test number 3. Next Monday, a week from today, I will go over test number 3 answers in our Zoom meeting, but I will delete this. I like my special effects. I'll delete this from the video, but I'll post a private video if you can't make it to next Monday's meeting. I will do a review of the material on test number 3 tomorrow in our Zoom meeting. And with that, have a great rest of the week and weekend, because I posted this. One was a Saturday at about noon. All right. So this Thursday, I will be giving test number 3. Speaking about tests, test number 2, you people did a great job. Thank you. Test number 2 is the hardest test of the semester. And I've had classes who've had averages of 68, 70, 72. This class, I think the average was 89. Thank you. Made my day, made my heart feel good, which is a good thing. Now, let me shut this, get back to full screen. I'm going to be, thank you, Judith. I'm going to be going through the answers to test number 2. Each of you received individual emails with the answers for, or points for each answer on test number 2 that you received. Make sure I graded things correctly. A student should never be penalized for a mistake I make on grading. Do I make mistakes once in a while? Yeah. I hate to break this to you, but I don't walk on water unless it's frozen. Even then I stay off it. In other words, everybody can make a mistake. I keep them to a minimum, but you should check. If there's a mistake in grading, email me, tell me what was the mistake, and I will go back and look and see if I did. If I did, you will get the points that you should have gotten, because no student should ever be penalized for a mistake I make. All right, let's go through this. Any questions about test number 2? Well, I'd have a question. What grade am I getting in your class, Dr. White? Good question. And there are 2 methods that you can consider. Both of these assume that you have handed in all the labs. Take the sum of your 2 test scores, divide it by 2, and you get a number X. If X is greater than or equal to 90, you're getting an A. Again, this assumes you've handed in, all the lab. If X is you're getting a B if it's 80, 89. $70 to $79, if X is that and you've handed your labs, you're getting a C. $60 to $69, if that's X and D. If it's less than or equal to 59, unfortunately, you're getting an F. Now, there's a second method. Since the lowest test is dropped of the 4 tests, get your test total. Y equals the higher score of the 2 tests. And just like above, if Y is greater than or equal to 90, you're getting an A. If Y is equal to 80 to 89, you're getting a B. If Y is 70 to 79, you're getting a C. If Y is equal to 60 to 69, you're getting a D. And if Y is less than or equal to 59, well, you're in bad shape. I hope nobody's there. You're getting an F. Again, this assumes you've handed in all your labs. All right, couple things. One, as I said earlier, bad Dr. White, bad Dr. White. I fell, that happens in the summer, not in fall and spring, but summer it does happen because there's a lot of labs I got to grade. And when I give a test, I'm a little behind my grading. By Thursday, I will catch up. Also, I didn't have time to put it out, but I will be doing a lab amnesty program. And I'll give you, that I can't see that calendar. Let me go to another one. All right, I will be giving everybody till August 1st to get any past labs in, because a lot of you had problems getting your kit, and it's been happening. It happened last semester too. I will do that amnesty. But future labs, you all should have your kit by now. Get them in on time. And one last announcement, because I've been busy today, I didn't have a chance to, but next day or two, I will be posting, are you ready for this? An extra credit project. There'll be 10 bonus points. And if you do the extra credit project and get it right, it's not that hard. You should be able to get it right. It's like getting 10 more points on any of your tests. It helps. All right. Any questions? Oops, that's not what I wanted to do. Opening some files, so please be patient. Hi, you're welcome, Judith. All right. I promised I would go through chapter 6 practice problems. So I'm going to keep my promise and do that right now. Then afterward, we'll go back to chapter 5, part 2 and finish that up. All right. That's not what I want. All right. Everybody should see the practice problems. Now, here I have how many? Let's do number 3. Or let's do number 2. How many millimeters of mercury is 1,245 torr? Now, you're asked to find millimeters of mercury. Hg is the chemical symbol for mercury. Torr, both of those are units of pressure. And here I have 1 millimeter mercury equal 1 torr. You're starting here. You want to get to here, use unit analysis. This goes on top, torr underneath. And also, if you look at, I have 1 and 1, but if you look at important information, test number 3, you'll see I give you 760 torr equals 760 millimeters mercury, same as saying 1 equals 1. but it also equals 1 atmosphere, ATM. Now, the ones or the 760 are exact numbers. Therefore, you start out with 4 significant figures, you end up with 4 significant figures. Let's look at number 3. How many ATM, that's atmospheres, is 741 torr? Trying to find atmospheres, ATM, you're given torr. Here's what you start with. You're trying to get to this. Use your good buddy, your good friend, unit analysis. Whatever you're trying to get to goes on top of the ratio. Whatever you're trying to get rid of goes underneath. You look at important information, I just showed you, but I also wrote it here. 1 atmosphere equals 760 torr equals 760 millimeters of mercury. 1 atmosphere, 760, these are exact numbers, 3 significant figures. You round your answer to 3 significant figures. Now, let's look at 4. How many torr is 1.237 atmospheres? We're trying to find torr. We're given atmospheres. Here's what we're starting. We want to go to this unit. Torr is our answer. Use unit analysis, your good buddy and your good friend has been mine for a long, long time. And whatever you're trying to get to goes on top of the ratio. Whatever you're trying to get rid of, ATM, goes underneath. You get the ratio right here, 1 atmosphere, 760 torr. Those are both exact numbers. Therefore, they do not play a role in determining significant figures. This does, that's 4, and your answer should have 4. Now, I've written it that way. It also could be 9.401 times 10 squared. All right, let's look at number 6. If a balloon has a pressure of 658 torr and a volume of 1.894 L, L is liters volume, what is the pressure of the balloon if the volume is increased to 5.133 liters? What are you trying to find? The pressure after you've made a change, which we call the final pressure, P2. What are you given? An initial pressure, P1. Initial volume, V1. And you change it to a final volume, V2. Notice here, all we are dealing with is pressure and volume. In case you forgot, you go to important information, test number 3, Boyle's law. P1 times V1 equals P2 times V2. P1, initial pressure. V1, initial volume. P2, final pressure. V2, final volume. Aren't you glad I'm not having you memorize this all like I used to in the past? This will be at the end of test number 3, important information. So we now know P1 times V1 equals P2 times V2. Here we have it. What do we need to solve for? P2, which means you want it alone on one side. Well, how do we get rid of V2? Well, when you have 2 things multiplying each other, if you divide by one of those things, anything divided by itself is number 1 is gone. But whatever you do to one side, you have to do to, oh, that's a new one. Which way did it go? Which way did it, never mind. Anyways, you got to do to both sides. So divide this side by V2, this side. V2 over V2 is 1 times P2 is P2. And that's equal to P1 V1 over V2. Now, I've just rewritten it going here. Put P2 on this side, the expression V1 times V2 over V2 here. I took the time to figure out excuse me, what's P1, V1, V2, put them in there. Notice liters cancels out, and we're left with torque. Yay, that's what we want. And we have two Angelicas. Wow, Angelica square. Are you two related? No, I'm just kidding. But anyways, 3 significant, 4, 4. Get the same number of significant figures as the answer as the number with the lowest, 3 significant figures, and that's our answer. Now, if we look at 7, it's the same problem or type of problem. If a piston, like in a piston in your car, plunger in a container, has a volume of 24.4 liters, excuse me, at 12.34 atmospheres, what's the volume of the piston when the pressure is reduced to 3.567? So we have to find the final volume. What is the volume when something is changed? And we call that V2. The initial pressure, P1, 12.34 atmospheres. Remember, ATM is pressure. So is mmHg and TORR, torque. Well, we're working with atmospheres. L is a volume. It's at 22.4 liters. And here we get the final pressure is 3.567. So we have pressure and volume. What do we do? Hold on. Somebody has a question. Oh no, your laptop kicked you out? Oh no, bad laptop. Tell your laptop Dr. White doesn't appreciate laptops being mean to his students. All right, so we have this pressure and volume. What do? You go to important information, test number 3, Boyle's law. P1 times V1 equals P2 times V2, P1, initial pressure, V1, initial volume, P2, final pressure, V2, final volume. And now, what are we solving for? V2, we want it alone on one side. How do we get rid of P2 when it's multiplied times V2? Divide by it, because anything divided by itself is number 1. But whatever you do to one side, we do to the other. This cancels out. We're left V2 equals P1 times V1 over P2. I rewrote it here. And now I can put in P1, V1, and P2. Atmospheres canceled out. We're left with liters. Yay. That's a volume. And here's the number you get. That could also be 7.75 times 10 to the first liters. And this is 4 significant, 4, 3. Your answer should have the same number of significant figures as the number with the fewest significant figures. Let's look at number 10. Ooh, this is a good one. If you burp 86.75 grams of CO2, carbon dioxide, gas at 545 millimeters of mercury of pressure at 34.6 degrees C, a temperature, then what is the volume of your burp? Bet you never thought you'd get into burps in chemistry. Well, in my class, you get into a lot of neat stuff. And we do get into burping. Because I'm trying to be polite, there's another way you get rid of gas, and I used to do problems with that too, but not today. All right, So we are trying to find a volume, V. We're given a weight. We're given a pressure. We're given a temperature. And we're given, it's time to take a 5-minute break. So you're just going to have to come back after the break to find out how I proceeded with that problem. So, a cliffhanger on Dr. White's chemistry class. I'll see you in 5. I'm getting up and stretching. Time to get going. All right, let's get back. Ooh, dust. Let's get back to our problem set. And the question was, if you burp 86.75 grams of CO2, carbon dioxide, at 545 millimeters of mercury and 34.6 degrees C, what's the volume of your burp? Well, you got a volume you're trying to find, V. You're given a weight, mmHg, or torr, or atmosphere, is a pressure, degrees C, temperature. And I'll talk about R in a second. Well, what do? Well, you look at important information, test number 3. And when you're not changing any of the variables, it stays the same, and it's a gas, you're going to be using PV equal nRT. And important information, P is pressure, but it has to be in atmospheres. V is volume in liters. I'll always give it to you in liters. N is the number of moles. We got grams. And T is temperature in Kelvin. Finally, R is the universal gas law constant. And that's 0.0821 atmospheres liter mole K. Now, one other thing which I have hidden up here, Kelvin equal degrees C plus 273. And good news, you didn't have to memorize that. So we have PV equal nRT. We're trying to find the volume. To get rid of the pressure, we divide by it. To divide P by P, you get the number 1 times V is V. And the other side, you also have to divide by P. And you get nRT over P. Now, P is the pressure, but it has to be in atmospheres. So we have 545 millimeters of mercury. We're trying to get the atmospheres. Use the conversion ratio. What goes on top, atmospheres. What goes underneath, millimeters of mercury. Where do we get that number? Those numbers? 760 millimeters of mercury, mmHg, equals 1 atmosphere. This is important information, test number 3. And therefore, we have 760. Here's the number. This is 3 significant. These are exact numbers. You have 3 significant figures. Now, once again, we're doing multiple calculations for an answer. You can round off at each step like I do, or do it at the end. I calculate both for a test. Now, second, we need temperature. Temperature has to be in Kelvin. Remember, that's degrees C plus 273. Degrees C, I forgot to put the C there, bad Dr. White, is 34.6. And here's the number you get. Remember, 273 is an exact number. This is 1 past the decimal. This is an exact number. You should have 1 past the decimal. All right, finally, what's N? That's the moles. And again, that's important information. Test number 3. Let's take a look. Maybe I'm lying to you. And I'm not. 1 mole of a compound equals the molecular weight of that compound in grams. And the molecular weight of that compound is the sum of all atomic weights in grams. And therefore, have grams of CO2. We're trying to get the moles of CO2. Use your good buddy, your good friend, unit analysis. Whatever we're trying to get to goes on top of the ratio, moles of CO2. We want to get rid of grams of CO2, that goes underneath. 1 mole equals the molecular weight of the compound. the molecular weight of carbon dioxide, CO2, 1 carbon, 2 oxygen. Each carbon is 12.0 atomic weight. Each oxygen, 16, that should be 0.0. Looks like a 6 was 0.0. 12.0, 32.0. It adds up to 44.0. This is 4 significant, exact number 3. You get the same number of significant figures to answer. It's the number that has the fewest significant figures. You're multiplying, dividing by. This case is 3, and I rounded off to 3. Are we done? Far from being done. We're trying to find volume. Volume equal nRT over P. I rewrote it here. N, we calculated right here. What's R? It's the universal gas law constant. If you look at important information, test number 3, I give you R right here. R is 0.0821 atmospheres, liters, mole K. Kelvin, we calculated right here. Atmospheres right here. Do the math. 3, 3, 4, 3 significant figures. You get this, which is unrealistic. 69.4 liters. That's almost 35 of those 2-liter bottles. Your lungs aren't that big, but it was fun to calculate. And you get the same answer both ways. I would ask you to look at number 11. Same thing. We're trying to find a tire contains 25.67 grams of nitrogen gas N2 at 26 degrees C, 705 torr. What's the volume of the nitrogen gas in the tire? Trying to find volume again. We're given a weight, a pressure, temperature. Use the ideal gas law, PV equal nRT. Solve for V by dividing P here to get rid of the P. So you have V alone. But whatever you do to one side, you have to do to the other. I did. And V equals nRT over P. But N is moles. You're given a weight. Weight to moles. Moles goes on top. Grams go underneath. Remember, 1 mole of a compound equals the molecular weight of that compound. You need the molecular weight of nitrogen gas. Ooh, the N2 fell off. Don't look, don't look. But anyways, 2 nitrogen, each one is 14.0 atomic weight, and that's 28.0. 3 significant, 4 exact number, 3 significant. Pressure, you convert from torr to atmospheres. Remember, 1 atmosphere, 760 torr. Exact number, 3. Kelvin in temperature, degrees C plus 273. That's 299. V equals nRT divided by P. N, R, temperature 299 Kelvin. Pressure in atmospheres 0.928. Do the math. 3 significant figures. That's 24.3 liters or 2.43 times 10 to the 1 liters. And if you round off the end or each step, you get it to both ways. Now, a few things I didn't put down there. You should remember, and that is for your car tires in the winter, PV equal nRT tells you in the winter you should check your car tires, because in the winter it gets real cold, temperature goes down. PV equal nRT. In your car tire, V, N, and R are constant. If temperature goes down, your pressure goes down. In the summer, you should always check them too when it gets real hot. Thankfully, In our area, we have it. If I were in Phoenix, I keep an eye on my car tires big time. I keep an eye on me and anybody else I know big time, because the heat they have is horrendous. I don't think the daytime temperature for the last 2 weeks has been under 100 degrees Fahrenheit. That happened here in Chicago, 95, and it killed a lot of people. So in the summer, temperature goes up, PV equal nRT, and your tires at V and R are constant. If the temperature goes up, the pressure will go up. You'll get a blowout, like if you blow a balloon too much and goes pop. And I saw that happen, not firsthand, but afterward, the leftovers of the tires on the road back in 1995, when I think it was 95, we had that massive heat wave here. All right, there's one other thing that you should know and remember. And what happens to the boiling point of water on the top of a high mountain? Remember, boiling point is when atmospheric pressure equals the vapor pressure of water, which is obtained by adding heat. You put it on a stove. Well, as you go up in altitude, on our planet, lower atmospheric pressure. Oops, forgot an O there. Did I tell you I was always the first one down the spelling bee? So with lower atmospheric pressure, you need less energy to get the vapor pressure to water equal to the atmospheric pressure. Therefore, the boiling point or temperature, also known as, of water, and the other liquid too, but water decreases. So if you go to the top of Mount Everest, the boiling point of water is going to be a lot lower than here in Chicagoland. If you go to the top of the Himalayas, which is the highest mountains in the world, the boiling point is really going to be lower than here in Chicagoland. All right. We're done with the problem set. Any questions? All right, let me close that. And I need to open this. And now let you see this. And that's chapter 5, part 2, solutions. And we talked about a solution. A solvent is the component present in the greatest amount, and the solute are the other components. And different types of solution, like the air you breathe, pop is a solution, gasoline is a solution, and so on. I talked about the concept light dissolves light. Things that are polar are soluble in polar things, and things that are nonpolar are soluble in nonpolar things. And just to remind you, what's polar? Water is the most polar substance in our world. And then salts like sodium chloride, and then alcohol or alcohols like ethanol, the drinking alcohol, or your rubbing alcohol. And nonpolar things you should know. And I'll abbreviate vegetable oil and also gasoline, Vaseline, baby oil, and grease and dirt. Those are all nonpolar. I'll teach you later on the semester, how do you get dirt off your hands with water? The answer is use soap. I'll teach you how that works later on. I talked about solubility, and I'll let you read this. And don't forget, aqueous solution is a solution, water is a solvent. And I talked about colloidal dispersion. And remember, colloidal dispersion, light goes through it, or I mean, solution of light goes through it. But if you have a colloidal dispersion, which is not a true solution, the particles that are suspended block the light, like you can't see the light coming through my hand. And by the way, this is a Hank Wang flashlight. It's great, makes great flashlights, and that's a colloidal dispersion. And examples you should know, at least one, milk, latex blade, or your blood. All right, now this is where I ended up last week. How do we describe solutions quantitatively? This is called concentration. Now, there are three main ways. First one, percent concentration. Click, next slide, switches off. And percent concentration, also called percent by mass, is mass of the solute divided by mass of the solution times 100. And the mass of the solution is the mass of the solute and solvent. The higher the percent concentration, the more the solute present. Again, click, switches off. Do I have time? I'm going to make time. I don't get any kickbacks from Walmart, but no, when I bought this house I live in years ago, I've been here for a long time. It's a great place to live, a great house. First time I mowed the lawn, Saturday morning, 8 a.m., go out there. I bought the house in August. So it was August when I mowed my lawn. I've been here about a week. And guess what happened? I got attacked everywhere by every mosquito in northern Illinois. Whoa, I got it, put my lawnmower away and said, I need a mosquito repellent. Now you're dealing with an organic chemist who knows what's the active ingredient in mosquito repellent. It's called DEET. It's an acronym for diethyl toluamide. And you can go look at the national brand like Off and their regular Family Care, they have different ones, but off, or you can look at Repel, which is the Walmart brand. Now, it's got 40% more weight than, at least when I went, the off-brand equivalent, and it was a lot cheaper. You can't see, well, and here you can't see it, but if you pick up the label, and here's where knowing concentration, percent mass is important. The off-brand had, I'm just making up a number now, but it was essentially double, 2% D. The Walmart brand, which was cheaper, they gave you more, was 4% D. And that means they had twice as much as the chemical that kept the mosquitoes off. Guess which I bought with? I went with the Walmart brand. It was less expensive, they gave you more, and there was more of the active ingredient. That's where you get the percent concentration. And guess what? It worked. I didn't get attacked. If you go in my utility room where I have a couple bottles, I think two, one I'm working off of, and I always have emergency backup. Before I do anything outside work, like I did this weekend, spray it all over me. And guess what? I don't get attacked by mosquitoes. Yay. All right, again, switches off for this one. Next one, percent volume. That's volume of the solution divided by volume, or solute divided by volume of the solution. Sorry to hear that, Yulia. I'm not allergic to that. Have you just tried, I guess the vapor would get you too. Some people are allergic to different chemicals. And luckily, that's something I'm not allergic to. I am allergic to wool. I just go like that when I'm, when I was young, gave me a wool sweater or socks, and I never wore wool again. Every time I've tried, All right. Now, where you normally see volume percent is in wine. The percent volume of wine is usually how much alcohol in wine. All right. For percent volume, percent or concentration by volume, click, switches off. If I had a dial for switch that I could turn to 10, for molarity, I've just turned it to 20. Molarity, it's a way of determining concentration, how much of a solute is in a given solution. We abbreviate molarity with a capital M. By definition, and you should know, molarity is moles of solute per 1 liter of a solution. I even have it typed here. Very important. Know this. Now, molarity, since 1 liter equals 1,000 milliliters, and therefore molarity, moles of liter, in the lab, we usually use moles per 1,000 milliliters. All right, molarity. moles of solute per 1,000 milliliters. The 1,000 is the exact number. The molarity, the moles of solute, well, however exact significant figures you have this. Now, good news, in the past, you would have to memorize this, but if you look at important information, test number test number 3, got ahead of myself. I have here molarity equals moles of solute per 1,000 milliliters of solution. And you should know how to use this. Let's talk about some important factors of molarity. If you were to go into the stock room of College DuPage chemistry department, we don't let students in there, but if you did, or some of the bottles in our lab, you'd see something like this. This on the label. And what does this mean? And say on a test, you were to see, what does this mean? 3.85 capital M NaCl. What does this mean? Or if you saw it on a label, that means molarity, moles of solute per 1,000 milliliters of solution. So that's 3.85 moles sodium chloride, NaCl, per 1,000 milliliters. That's what that means. Here's one for you. B. What does 8.96 capital M HCl mean? I'll give you time and then I'll do it. Remember, M, molarity, moles of solute per 1,000 milliliters. The question is, what does that mean? And it's my turn. Whenever you see capital M with a number on one side and a formula on the other, that means molarity. Molarity, moles of solute per 1,000 milliliters. So what does this mean? .967 moles of HCl per 1,000 milliliters of solution. Now, let's do another one that you should know. And the question is, what does this mean? And what is the solution of the solvent of the solution? And I'll do this one. As soon as you see capital M, that's molarity. My nose itches, sorry. And molarity, moles of solute per 1,000 milliliters of solution. So as soon as we see this, what does it mean? 3.61 times 10 to the squared moles, and NaOH is sodium hydroxide, per 1,000 milliliters of solution. But what's the solvent? This tells you whenever you see bracket AQ close bracket, that means solvent is water. Therefore, and solvent is water. And let's have you try one. And B is 2.3 times 10 to the minus 2, capital M, sugar, bracket AQ, close bracket. And question is, what does this mean? And what is the solvent? Your turn. And I forgot to fire off the poll, it's called. There we go. All right, my turn. As soon as you see a number, capital M, and a formula or the name of a compound, that tells you molarity. And molarity is moles of solute per 1,000 milliliters. So what does this mean? It means, oops, I lost part of my arrow there. 2.3 times 10 to the minus 2 moles sugar per 1,000 milliliters. That's what molarity is. But what's the solvent? And bracket AQ bracket means the solvent is water. Now, what makes molarity so important to chemists? And it is, it's been important in my career. It allows you to do important things. And that was not where I wanted to go. Let's try the third thing if I can get it right. Example would be questions that molarity can help you answer. How many moles of a solute are in X milliliters of a known molar solution? SLN is shorthand for solution. I forgot, I didn't even realize I was doing that. Shouldn't use abbreviations, but anyways, All right, 8 points or maybe 6 points, depending on my mood. How many moles KBr are in 385 milliliters of a 1.773 molar KBr solution? Well, what do you do? Well, what are we being asked to find? Moles of KBr, potassium bromide. What are we given? Well, two things. A volume of the solution and this number. And before I go any further, I see this capital M and I say to myself, what does that mean? That means 1.773 moles of KBr, potassium bromide, per 1,000 milliliters of solution. Now, the main number I have to work with is this. And if I had a ratio, what units do I want my answer to be in? Right here. And guess what time it is? Yep, you're right. It's time to use your good buddy, your good friend, unit analysis. Whatever we're trying to get to the units, go on top of the ratio. Whatever we're trying to get rid of, go underneath. And now we have moles of KBr and milliliters of solution. And where do we get these numbers? From right here. We knew what the M means, molarity, which means this. And we know there's 1.773 moles of KBr, potassium bromide, per 1,000 milliliters. And notice milliliters divided by milliliters equal 1, because anything divided by itself equals the number 1, cancel out. We're left with moles of KBr. And now I'll pick up my calculator, turn it on, clear it. And my calculator gives me this number. And if we look at this as a multiplication division, you get the same number of significant figures in your answer as the number you're multiplying and dividing. As a few significant figures, 3 significant figures, all non-zero numbers are significant, 4 significant figures. And the 1,000 is a part of the definition, so that's an exact number. Therefore, I should round this off to 3 significant figures. Keep the 6, keep the 8, keep the 2, use the 6 to round off, drop that, increase that by 1. And the correct answer is 6.8. Let me rewrite that. 6.83 times 10 to the minus 1 moles of KBr. Now, what this allows you to do is take a known stock solution like 1.773 molar KBr, and when you know that molarity, you can calculate if I needed a certain amount of moles, I could just measure out this number. And that makes it easier. You have a bunch of stock solutions, or in a plant, we have drums of them, or totes, which are 2,000 pounds, or I forgot how much, let's hold on, 200 gallons, I'm sorry, 200 gallons of a stock solution. You measure out a certain amount to get the moles you need. Well, that was fun. Let's do it again. We got something important. All right. How many milliliters, ml is milliliters, of a 3.75 capital M H2SO4, that's sulfuric acid solution, is needed to obtain 2.34 times 10 to the minus 1 moles of H2SO4. Now, let's do this stepwise. First of all, I'm going to ask you to figure out what are you trying to find and what are you given? Again, all I'm asking you to do is find out what are you trying to find and what are you given? All right, my turn. And thank you for letting me have my turn too. All right, what are we trying to find? How many milliliters of a solution? What are we given? Well, we have 2.34 times 10 to the minus 1 mole of H2SO4. And the other thing is we're given this number, 3.75 capital M H2SO4. As soon as I see the capital M, that means molarity. And what does that mean? I'm going to let you do this one, then I'll show you. What does 3.75 capital M H2SO4 mean? I don't know if I reset it. I'll do it again. And someone already got it right. And I bet somebody else did too. Capital M, molarity, moles of solute, 3.75 moles of sulfuric acid per 1,000 milliliters. Now, the main number we have to work with is this. So I'll move down here because I need more room. 2.34 times 10 to the minus 1 moles. And what units do we want our answer to be in? Milliliters. Now, I'm going to let you figure out what number and what unit go on top and bottom of the ratio, and then I'll do it. And don't forget, use your good buddy, your good friend. It will help. All I'm asking you to do is what number and what units go on top and bottom of that ratio. All right. Everybody's done, so I better get to work. Time to use your good buddy or good friend unit analysis. Whatever we're trying to get to goes on top of the ratio. Whatever we're trying to get rid of goes underneath. And there I have the units. And where do I get these? From molarity. For every 1,000 milliliters, there's 3.75 moles of sulfuric acid. And moles divided by moles of sulfuric cancel out because anything divided by itself equals the number 1. And I'm left with milliliters. So now pick up my calculator, clear it, 2.34 blue double E, the minus sign on the keyboard, minus 1 times 1,000 divided by 3.75. And the number it gives me is 6.24 times 10 to the 1 milliliters, which is also 62.4 milliliters. And don't forget, you get the same number of significant figures to answer as the number that has the fewest significant figures. This is 3 significant figures. All non-zero numbers are significant. 3 significant figures. Oh no, he's in his 3 significant figure. Right. And the 1,000 is the definition per 1,000 exact number. And our answer should be 3 significant figures. And it is. Now, I'm going to go and do one more problem. We're going to go a little over time, and tomorrow I'll do some more of these, but I want to get one in right now. And one of the most important things to having stock solutions like 3.75 molar H2SO4 is making them. And that's an important thing. All right, 10 points. Yep, 10 big ones. How many grams? Remember, G is grams, NaOH, sodium hydroxide. I apologize for going a little over today, but I want to get this in today. How many grams NaOH are needed to make 386 milliliters of a 1.22 capital M NaOH solution? What are we being asked to find? Grams of NaOH. What are we given? 368 milliliters we're trying to make. And we're given this right here, 1.22 capital M NaOH. Now, as soon as I see capital M, I know that's molarity. And what this really means is 1.22 moles NaOH per 1,000 milliliters. Now, if you're using an analysis, you would find there's no way in one step I can go from milliliters to grams. There's no way in one step I can go from milliliters to grams. So what do? Well, you look at important information, test number 3, and that's the molarity two-step problem. Step 1, milliliters to moles. Step 2, moles to grams. Again, you need two. Anybody getting dizzy? 2 steps. So let's do it. So you need 2 steps. Step number 1, milliliters to moles. So what do we have? Well, we have 386 milliliters. We want to go to moles of the compound we're dealing with, NaOH. And now you'll use your good buddy, your good friend, unit analysis. Whatever we're trying to get to goes on top of the ratio. Whatever we're trying to get rid of goes underneath. So I'll write it in there, moles, NaOH, sodium hydroxide, and milliliters. Oops, use cursive. Milliliters. And where do we get those numbers? We knew the molarity here really meant 1.22 moles of sodium hydroxide per 1,000 milliliters. And now milliliters, well, I've got it twice. Hold on. Milliliters cancel out. Anything divided by self is number 1. We're left with moles of NaOH. So I'll pick up my calculator, clear it. 386 times 1.22 divided by 1,000 equal 4.709 10 to the minus 1. Remember, when you're multiplying, dividing, you get the same number of significant figures in your answer as number that has fewest. 3 significant figures. Oh, he's in his 3 significant figure rut. And the 1,000 is an exact number. Therefore, my answer should be 3 significant figures at this step, which means keep the 4, keep the 7, keep the 0, use the 9 to round off. Is that 4 or less or 5 or higher? 5 or higher. Drop those, increase that by 1. So right now we have 4.71 times 10 to the minus 1 moles NaOH. But we're trying to get to grams of NaOH. So we need the second step. This was step 1. We'll now do step 2. which hopefully you learned this step for test 2, but it'll also be needed for test 3. We want to go from moles to grams of a compound. And we just in step 1, step 3, step 2, I'm sorry. See what happens when you rush, you make mistakes. Step 2 is moles to grams. We just calculated we have 4.71 times 10 to the minus 1 moles NaOH. And we want to get to grams of NaOH. So we'll use our good buddy, our good friend, unit analysis. Whatever we're trying to get to goes on top of the ratio. Whatever we're trying to get rid of goes underneath. I'll write that in. And where do we get the relationship between moles of a compound and grams of a compound? Well, in case you forgot, important information, test 3, 1 mole of a compound equals the molecular weight of that compound in grams, and the molecular weight is the sum of all atomic weights. Well, we need the molecular for every 1 mole of sodium hydroxide. We need the molecular weight here of sodium hydroxide. And that's the sum of all atomic weights. Molecular weight of sodium hydroxide, 1 sodium, 1 oxygen, 1 hydrogen. Remember, the atomic number, the number underneath the chemical symbol, is the atomic weight, the 3 significant figures. Sodium is that, oxygen is this, hydrogen is this. I'll add them together. This is 1 past the decimal to the right, 1, 2. You get the same number of significant figures to the right of the decimal as the number with the lowest significant figures. So I'll keep the 1, keep the 0, use the 1 to round off as 4 or less. So this is 40.0. And now I'll pick up my calculator. I have 4.71 blue double E minus 1 times 40.0. And my calculator gives me 1.884 times 10 to the first. Don't forget the little 10 to the power number. And when you do a multiplication division, there's 3 significant figures, 3 significant figures, always in a rut again, and exact number. And you get the same number of significant figures as the number you multiply and divide. As the lowest, in this case, they're both 3. Keep the 1, keep the 8, keep the 8. Use the 4 to round off. Is that 4 or less? And it is a 4, so it's 4 or less. Drop that. And the correct answer is 1.88 times 10 to the 1 grams of sodium hydroxide. And if I put this in and make a solution of total weight of or volume of 386, this is the molar solution I will make. And this is an important calculation chemists do in the lab and plant. Now, don't forget, tonight at 7 to 8, I will have my office hour. Don't forget tomorrow, we're going to have our lab, and we will also go through test number 3 review. And I'll do a couple more of these problems I just did with molarity. And with that, don't forget, hand in labs, they're easy points. And with that, I'll say, unless anybody has any questions and want to stick around after class, which I will, I'll say, thanks for letting me go a couple minutes later today. Gang gesund. That means Yiddish, go in health. Gang gesund. Bye now.